Okay, let's continue on chapter 7. Today we're going to talk about trigonometric integrals. There are certain identities that we should know about trigonometric functions. The simple one is the Pythagorean identity: sine squared plus cosine squared equals to 1. And if you divide both sides by cosine squared, you would get tangent squared plus 1 equals secant squared. And similarly, if you divide the first equation by sine squared, you would get cotangent squared plus 1 equals cosecant squared. You should have seen this already in Calc 1. Then we have the half angle identity, which you can write the the second power sine squared in terms of cosine of 2x. It's a backward double angle. So basically through the double angle you will end up with this half angle equality. And similarly for cosine squared x, you can get 1/2 plus 1 times cosine 2x. It's not x anymore, it's 2x. The angles would be doubled. And if you have product of sine and cosine, you can write it in addition of sine and cosine. So here if you have sine times cosine, you can write the sine difference of the angles, a minus b, plus sine sum of the angles, a plus b. This is in case if we deal with sine 2x cosine of 3x, in which the angles inside are not exactly the same thing. We use this identity. And similarly, if you have sine times sine, you would use this identity of, by the way, the 1/2 is a coefficient for all of them. Cosine a minus b minus cosine a plus b. The good thing is you don't need to memorize these. These are all available throughout the exams and quizzes, but you should be able to see how you can use these, and we're going to discuss that today. Okay, so let's focus on a simple integral. Let's say you're given sine squared x times cosine x dx. And through our integration techniques, we can test to see if we can use substitution or simple integration if possible. If that's not possible, then use integration by parts. So in this case, sorry about that, substitution will work easily. Anytime you look at the product of sine and cosine, first you check to see if the angles are the same. In this case, you have sine x times cosine x, which means the angles are exactly the same thing. In that case, what you need to do is just to create one of the trigonometric function, either sine and cosine, to have power 1. If you do that, then what you can simply do is use substitution. The u equals sine x, and then the derivative of the u would be du would be simply derivative of sine is cosine x, and multiply both sides by dx, so you get cosine x dx. And now, if you go back, look at the integral could be written as, instead of sine, we have u, so u squared. Instead of cosine x dx, that is simply our du. And what is this integral? This integral is simply a power rule. You add the 1 to the exponent, divide by the same thing. So u cubed divided by 3 plus some constancy. So therefore the integral results in u, which is sine, so sine x to the third power divided by 3 plus some constancy. And you notice it's very simple. As long as you have a trigonometric function to power 1, then you can always pick the other trigonometric function to be the substitution. I didn't pick the power 2, it's just simply the sine is what I picked as the substitution. Okay, let's look at another example. Let's say, what if we had the case where we have only cosine cube and there is no sine? Normally in these cases you try to create that to 1 power, if possible. In case if the degree is odd, that's always possible. So if you have cosine cube, you can assume, by the way, through the Pythagorean identity, we know cosine squared x equals 1 minus sine squared x. If I subtract sine squared from both sides of the trigonometric identity here, the Pythagorean identity, you will get cosine squared equals 1 minus sine squared. Similarly, you would have sine squared x would be 1 minus cosine squared x. The same idea will hold for secant, tangent, cotangent, and cosecant. Okay, so instead of cosine cube, the technique would be to write this. Let me write the solution in a different color. Let me use green. Okay, so the technique would be, instead of cosine cube, you would write it as cosine x to second power multiplied by cosine x. Okay, what did I do is I just created the one single cosine by itself, and everything else would be cosine squared, because this product is simply cosine cube. So the purpose here was to create that cosine, single cosine to power 1. And then instead of cosine squared, through this identity, I can write this as integral 1 minus sine squared x instead of the cosine squared, and multiply by cosine x. If this was to the power 20, I could write this to the power 2, the whole thing to the power 10. You can always do this. Okay, so as long as the cosine single, you can create some even power multiplied by odd power, you can always do this identity. So dx, and here we have a product, and I can use the technique that we discussed in the last example. I will pick a substitution, u to be sine x, and what is du? Du would be cosine x dx. And I can write this equality as integral 1 minus sine squared becomes 1 minus u squared, and instead of cosine x dx, that is simply du. Du is cosine x dx. So the integral we have is integral 1 minus u squared du, which becomes a simple integration. What is the integral of 1? Is u. What is the integral of u squared? Would be minus u cubed over 3, plus some constancy. If there were boundaries, you can evaluate. If there was a boundary like from 0 to pi, you can change the boundaries as well, or you can evaluate at the very end. Those are from the Calc 1. You can always refresh your memory over those. Okay, so here u was sine x, so I have sine x minus sine cube x divided by 3, plus some constancy. And this is the solution to that integration. You notice the whole thing, the technique is to create, sorry, there is a dx here that I forgot. The whole purpose is to create this cosine single in which the other terms have even power. If they have even power, if it's only sine doesn't really matter if it's odd or even. But if it's cosine squared, you try to use this identity, this Pythagorean identity, to write in terms of sine. Okay, how about this one? We dealt with cosine cube. What if we had cosine to the 4th power? Now, if you try to create what we did and say I have cosine cube x times cosine x dx, then sure, this is the part you want as the derivative, but the cosine cube, we don't have any identity for that. We have cosine squared x times cosine x times cosine x dx. And what this causes is you can use substitution and change this to, not substitution, through the identity, and write that as 1 minus sine squared x. Then what do we do with this cosine? That doesn't go away because we don't really know any identity for this one. So what do we do in this case? It's kind of, this idea doesn't really work. So we have to come up with a new way to calculate this integration. So if you deal with the odd power, it's okay. You can go through the technique. If it's a combination of sine and cosine where one of them has odd power, that's always possible. But if you're dealing with even powers, like cosine to the 4th power, what you need to do is use this half angle identity. So instead of cosine squared, I have this identity 1/2 1 plus cosine 2x. So what I'm going to do is I try to write this in terms of integral of cosine squared x to the power 2. That's the same as cosine to the 4th power. And what do I know is cosine squared is simply 1/2 1 plus cosine 2x. And this whole thing is to the 2nd power. Okay, so the identity that we used is cosine squared x is exactly the same as 1/2 1 plus cosine 2x. And the 2nd power is still out there, dx. Okay, let's simplify it. 1/2 to the power 2 is simply 1/4. It's a constant multiply, so you can write it outside if you want. 1 plus cosine 2x to the 2nd power, dx. And I will continue simplifying this. I'll write it as 1/4. The integral of 1 plus cosine squared, cosine 2x squared is basically, you write it twice multiplied by itself. So I can do that up here, just to make sure everyone follows. I'm going to write it here. 1 plus cosine 2x squared would be 1 plus cosine 2x multiplied by 1 plus cosine 2x, and then you distribute. This times that, and so on. So what you get is 1 plus 2 cosine 2x. Be careful, this 2 does not multiply inside, and you have cosine 2x times cosine 2x, that is the same as cosine squared of 2x. It's not cosine 2x squared. It is the cosine function multiplied by itself. The input, the angles are fixed. So I can write this integral now. What do I have is 1/4. 1 plus 2 cosine 2x plus cosine squared 2x dx. Maybe use a bracket here. Okay. Again, one more issue that we're dealing with is at this point, this term has even power. This one is an odd power, so no problem, we can calculate the integration of that. The even power, similar to cosine 4th to the power 4x, again would be difficult to calculate that integral. So what I'm going to do is I'm going to try to redo exactly what I did. I have 1 plus 2 cosine 2x, and the identity that we used was cosine squared of x equals 1/2 1 plus cosine 2x. So if the angle inside, if instead of x here, if the angle was, let's say 2x, what would happen is every x will change to 2x. So this would be 2 times 2x. So basically it becomes 4x. So instead of cosine squared 2x, I can write 1/2 1 plus cosine 2 times 2x would be simply 4x. And that is our substitution for the cosine squared 2x dx. Let's try to simplify all these. So you have 1, and let me actually highlight these. You would have 1 times 1/2, that is 1/2, and here plus 1, so it would be 3/2. So I have 1/4 outside multiplied by the integral of 3/2 plus you have 2 cosine 2x, 2 cosine 2x, and plus 1/2 times cosine 4x, 1/2 cosine 4x, and this whole thing multiplied by dx. Okay, so let's before we calculate the integral, let's try one more thing, because it's necessity. Then that you should know how to calculate these integrals. I'm going to do one of them, maybe up here. If I ask you to calculate cosine, let's say 4x dx, the integral of that, what you can do is always, you can use substitution and call this inside to be your substitution. So you can say u equals 4x, therefore du equals, take a derivative for dx. We're taking derivative from both sides. So this integral becomes cosine of u multiplied by, instead of dx, you should divide both sides by 4. So this will cancel out. You will get dx to be du over 4, or 1/4 du. Then the integral simply becomes 1/4. What is the integral of cosine? This can come out and write cosine u du. What is the integral of cosine? It is sine u plus some constancy. So what is the u? U was 4x. So we have integral of sine 4x plus some constancy. Okay, so I can calculate this integral, cosine 4x, by doing that substitution. Similarly, you should do a substitution for cosine 2x. And what you would get is 1/2 sine 2x. So basically, I can calculate the integral and say, okay, the result of this integral, I have a 1/4 outside. Integral 3/2 would be 3/2 x. That's a fixed value, constant. The integral would be 3/2 x. The integral of 2 cosine 2x should be plus 2 times. The integral of cosine 2x is 1/2 sine 2x. And the integral of cosine 4x, we calculated it as, the 1/2 is still there. It is 1/4 sine 4x. And all this plus some constancy. The final simplified version of this would be 1/4 times 3/2 x would be 3/8x plus 1/4 times 1, so you'd get 1/4 sine 2x plus 1/4 times 1/2 times 1/4, that is 1/32 sine 4x plus c. This is the integral of that cosine 4x. Even though the question looks very easy, but you have to calculate all this. Just make sure that as a practice that you know how to calculate. Try to calculate this cosine 2x integration by doing similarly what I did up here. By doing exactly what I did here. Instead of 4x, you would have 2x. Okay, so this is in case if you have even powers and there is no odd power involved. If there is odd power, you can use those Pythagorean identity. So generally, this is the strategy that we deal with. If you have products of sine and cosine, where the angles are equal, they both have x, 2x, 3x, whatever that angle is inside. You look at the powers. So we focus on the powers, m and n. If one of these powers are odd, if m or n, one of them are odd, then you reduce that corresponding power to be 1. Make it power 1 by writing, for example, if it was cosine to the third power, write cosine squared times cosine to the power 1. And that cosine to the power 1, you can use the trigonometric Pythagorean identity to turn it into sine. After you do that, then you use substitution. Let u equals whatever the other one is. So let's say u equals to, in case here, if the power is cosine to the power 1x, then we let u to be the substitution sine x. If it was sine to the power 1x, the odd power, then you pick the substitution to be cosine x. Okay, so I didn't really specify use sine or cosine just because we don't know which one is the power. So the corresponding term that has power 1, you pick the other function to be your substitution. What if they both have even power? Then in that case, you do exactly what I did for the cosine to the fourth power. You try to reduce it by doing half angle. You reduce all those. Either they all will end up to be power 1, or you will have one odd power. If odd power shows up, then you go back to this part and use that. So let's see, for example, what if instead of cosine to the fourth power, you were dealing with sine squared times cosine squared x, where they're both even. This is like the second case, because the first case we did the example of that. What if you're dealing with the second case? In this one, what we need to do is we need to do half angle. So instead of sine squared, sorry about that, let me go with the green. Instead of sine squared, what I'm going to do is I'm going to write the half angle for the sine squared. It is 1/2 1 minus cosine 2x. And instead of cosine squared, I will reduce it to 1/2 1 plus cosine 2x and dx. Okay, let's distribute. 1/2 and 1/2, you can multiply, you get 1/4. That's the constant. Now if I multiply this parentheses by that one, you should distribute term by term. 1 times 1, 1 times cosine 2x, negative cosine 2x times 1, and negative cosine 2x times cosine 2x. So what do you end up with after simplification? You'll end up with 1 minus cosine 2x to the second power, dx. Make sure that you get this through the multiplication. It is important that you multiply properly, otherwise you will make the result would be incorrect. Okay, so you would have 1/4 integral. Integral of 1 is not an issue, so I can calculate that integral. The problem would be, again, now to deal with this cosine to this even power. So what do we do with that? You can always go back and say, okay, I have an even power. I will have the property to use the half angle. So I'll use the half angle again. Instead of cosine squared 2x, I will write 1/2 1 plus cosine of the angle would be doubled again. So 4x. Every time you reduce the power, the angle will get doubled. Dx. Finally, now we ended up with a cosine where the power is simply 1. Sorry about these parentheses. Okay. So you still have 1/4. I'm going to simplify the inside. You have 1 minus 1/2 times 1 is 1/2. So 1 minus 1/2 is simply 1/2. And you would have minus 1/2 times cosine 4x. So minus 1/2 times cosine 4x dx. And make sure to put a bracket so the dx is multiplied by everything. Okay, 1/4 is outside. Integral of 1/2 x. What is the integral of cosine 4x? We did this just earlier on. Remember this substitution cosine 4x right here. And the result became 1/4 sine 4x. So the integral of cosine 4x is the negative 1/2 is still there. Multiply by 1/4 sine 4x. And that is the integration at the end plus some constancy. You can always try to simplify. 1/8 x minus 1/32 sine 4x plus some constancy. Okay, so this is the integration technique if you're dealing with the product of sine and cosine, generally where the angles are equal. Okay, try to write example for yourself and do those. What if we're dealing with tangent or cotangent? If I talk about tangent, then cotangent would be exactly the same idea. So let's mainly focus on the tangent. First, let's figure out what is the integral of tangent. If you don't know this, you should always try to rewrite the integral in terms of sine and cosine. So the integral of tangent would be the same as integral of sine x divided by cosine x dx. Okay, it doesn't look that easy, but if you pick a substitution, u equal to the denominator, cosine x. Derivative of u would be, derivative of cosine x is negative sine x dx. Then this integral basically simplifies to integral, you have the numerator sine x dx. That is simply du. Instead of sine x dx, I can write du. I just picked a 1. I left a 1 here, so we know it's 1 times du. Actually, it's supposed to be negative. Sorry, negative 1, because we still have this negative. We require a negative times sine x. And what is the denominator? The denominator is simply u. So you have negative 1 divided by u times du. Okay. Can we calculate this integral? That is simply negative. The integral of 1 over u is ln absolute value of u plus some constancy. So this integral is minus ln absolute value of cosine x plus some constancy. So if they ask you what is the integral of tangent x, you don't need to go back every time to calculate this. You can simply say, okay, I know the integral of tangent. This is one of those cases when it's good to know the integral. But if you forget it, you can always go through this step and calculate. So I'm going to make this as a note, and we will use this in our calculation. So I'm not going to calculate this integral over and over. Similarly, what if you deal with secant? It turns out secant is quite tricky, so let me show you the idea. If you have the integral of secant, the trick is to multiply something. And if you ask me how do they come up with this, I think it would be through trial and error. So you try to create something that you already know the derivative or the antiderivative. For example, if it was secant squared, we would know the integral would be tangent. If it was secant tangent, we knew the integral would be secant. So the combination of those is what we're going to multiply. We're going to multiply a secant x plus tangent x in the numerator. And also in the denominator, I'm going to multiply exactly the same thing. So this way we haven't changed anything about the secant. It's like multiplying 1. But now if you multiply this secant to the numerator, what you get is integral. Let's write this, secant squared x plus secant x tangent x. And the denominator is secant x plus tangent x dx. Now look at this. If you have tangent, what is the derivative? It is secant squared. If you have secant, what is the derivative? Secant tangent. The whole purpose of this multiplication was to create something like this. Now I can do a substitution. Let u be the denominator. Secant x plus tangent x. What would be du? Du, the derivative of secant would be secant x times tangent x. And what would be the derivative of tangent? It would be secant squared x times dx. So this whole numerator multiplied by dx, this is just du. And so I can write this integral equals to integral. Instead of the numerator, I can write 1 du, or simply du outside, the same thing. And the denominator, we call it du. And what is this integral? The integral of 1 over u du, it's ln, absolute value of u, plus some constancy. And then what is ln? Instead of u, you would have secant x, because we called u to be secant x plus tangent x, plus some constancy. So it's quite difficult without knowing this trick. And here, so I'm going to make the second note to be that the integral of secant x by itself, without any power, it's simply ln absolute value of secant x plus tangent x. Again, you can use this without going through this process over and over. In your homeworks, in your exams, this is totally fine. Okay, so we consider knowing these two, then we try to calculate more complicated integrals. What if there was power involved, something like tangent to the third power? If you remember if you had sine to the third power, what we did is we tried to reduce it to one term with the power 1, everything else with the even power. Everything else would have like the other function, the other trigonometric function. You would have sine to the fourth power multiplied by cosine to the 1 power. So similarly, what I'm going to do is I'm going to use the identity, the Pythagorean identity, that where tangent squared x plus 1 equals to secant squared x. So therefore, what is tangent squared? It is secant squared x minus 1. I'm going to use this identity to somehow reduce this power to tangent squared x multiplied by tangent first. That's exactly the same as tangent cube. And instead of tangent squared, what I can write is integral secant squared x minus 1 multiplied by tangent x dx. Okay, you might ask, what is the use of this? It doesn't look like the derivative of tangent is not secant squared minus 1. It is only secant squared. So what do we do with that negative 1? So here, what I'm going to do is I'm going to write this as tangent. Let's multiply the tangent. You will get tangent x times secant squared x minus tangent x dx. But I can write this as two different integrals. One is tangent x secant squared x dx. The other one is the integral of just simply tangent x. So I split it up because I want to use substitution for the first one, and the second one doesn't really require substitution. I already know that integral. We already know the integral of tangent x. We calculated above. And for this tangent x secant squared x, what I'm going to do is I'm going to pick a substitution. So we know this integral, and the result is minus, okay, let's do it in the next line. Okay, so let's first calculate this integral of tangent x secant squared x. What would be the integral? So the integral of tangent x secant squared x dx. The substitution that I'm going to pick, since I know the derivative of tangent is secant squared, so I'm going to let u be equal to tangent x. Then du would be simply secant squared x dx. And what do we have? We have the integral of u multiplied by the secant squared x dx is simply du. And that integral is u squared over 2 by power rule plus some constancy. So what is this? A u squared, the u squared would be tangent squared x divided by 2 plus some constancy. So I calculated this integral as well. These two are exactly the same. And that's the result. So finally, I can go back and say the result of this integral, it would be, the first one will give us tangent squared x over 2 plus some constant c. I'm going to combine those constant c minus the integral of tangent x dx. We calculated that it was negative ln absolute value of cosine x. It was one of the notes that we mentioned above. And negative is simply positive, so plus and plus some constancy. And here, this is the result of that tangent to the third power. So the technique is similar to what we did for sine and cosine, except that when sometimes you deal with single tangent or single secant, then in that case you need to know those integrals, the two integrals that we mentioned as notes. Okay, what if it was secant to the third power? Would the substitution work here? If we go through the same idea and say, okay, I'm going to write secant as secant squared x times secant x dx, and then change secant squared to secant squared would be 1 plus tangent squared x, and you would have times secant x dx. The problem here is that if you pick secant to be the substitution u, the derivative is secant squared. It's not tangent squared. Sorry, it would be secant tangent. It's not tangent squared. And if you pick tangent to be the substitution, then the derivative would be secant squared, not secant. So the substitution in this case does not work if you're dealing with secant to the odd power. If it was tangent to the odd power, then you could go exactly do what we did earlier on. But if you deal with secant to the third power, turns out it requires integration by part. So what I'm going to do is I'm going to write this secant to the second power x multiplied by secant x dx. And what do we know? We know that this is secant squared is the derivative of tangent squared. So it's not tangent squared, just tangent. So what I'm going to do is I'm going to say, okay, let's use integration by part. Let the u be the secant x, and let dv equal to secant squared x dx. So then what is v? What is du? Du, the derivative of secant, would be simply secant x tangent x dx, and the derivative, the integral of secant squared x dx, to figure out what is v, the integral of secant squared would be simply tangent x. So now, if I know these two, integration by part would be very simple. I can say this equals uv minus integral of v du, because I assume this is u times, I assume this is u times dv. Okay, so instead of u, I have secant x. Instead of v, I have tangent x. So I have secant x times tangent x minus the integral of v du. V is tangent x. What is du? It is secant x times tangent x dx. And this is secant x times tangent x minus the integral of secant times secant x, secant x times tangent squared x dx. Again, here we have a dilemma. And what is the dilemma? The dilemma is that the integral of secant x tangent square x is not that easy, because the derivative of secant is not tangent square, neither the derivative of tangent is secant by itself. So what we need to do is maybe do integration by part one more time, or rewrite tangent squared somehow. What if we rewrite tangent squared? Because we already know what is tangent squared. What do we get? We get secant x times tangent x minus the integral of secant x. What if we write tangent squared in terms of secant? Remember that 1 plus tangent squared was secant squared. So secant squared minus 1 would be simply tangent squared dx. And here we go. What do we have? We have secant x tangent x minus, I know this might look like it's too much, But after you do similar example, you will notice that the idea is always the same. So here, if I distribute, what you get is secant cube x dx, and secant times -1 would be minus secant. So you'll get, let me write them next to each other, then we will separate them. Secant x dx. Okay. Finally, I'm going to write this as two separate integrals. So you get secant x tangent x minus integral of secant cube x dx, and plus integral of secant x dx. The minus becomes positive. Okay, here is one thing that you should be kind of aware of. Where did we start with? We started with the integral of secant cube x dx. And where did we end up? We end up with more complicated terms, and here again we have that term secant cube x dx. So you may think we didn't make any progress. But the thing that you should be aware of that is, if I ask you that star equals 2 minus star plus 5, how would you find the star is that you add star to both sides, and what you get is 2 star on the right side, left side, and on the right side you have 2 plus 5, maybe 7, if possible to adding. Then star would be simply 7 over 2. What you see here is, if I call this star, you see exactly star equals some term minus star plus some other term, exactly similar to this idea. So what you can do is try to figure out that integral by itself by moving it to the other side. So I'm going to write this equality down here just to make sure that everyone follows. We started with this integral of secant cube x dx, and where did we end up? We ended up with secant x tangent x minus the integral of secant cube x dx, and plus, by the way, we know the integral of secant x dx, that one we already learned that it is ln absolute value of secant x plus tangent x, plus some constancy. You can add this constant later on if you want, but that's okay. So here, how do I get rid of this term? I will add it to both sides. So if I move it to the other side, what do I get is I get 2 of these integrals. And then to get rid of that 2, I'll divide both sides by 2. So basically you can figure out what is the integral of secant cube x dx. You'll get 2 of them. It equals to secant x tangent x plus ln absolute value of secant x plus tangent x, and plus some constancy. So if the question was find the 2 times this integral, this is what we get. But the question is find the integral of just secant cube. So it will be this guy divided by 2, this one divided by 2. Constant divided by 2c doesn't really matter. That's still a constant. So finally, we figured out what is the integral of secant cube x dx. This is the integral. And the tactic was similar to normally what you do for the integration by part, that you go back to the same term, but with the opposite side. So you move it to the other side and divide by 2. Okay. Generally, this is the case when you're dealing with secant to the odd power. If it was even power, we could have done, we could have dealt with it in a simpler way. So let's see the strategy behind this combination of tangent and secant. if you have tangent multiplied by secant, you look at the powers, m and n. So if the power corresponding to secant is even, if that's one of the cases, if this power is even, that means it's going to be a derivative of tangent at some point. If you try to reduce that power to be 2, so you want to create some secant square x, and everything else you want to leave it in terms of tangent. Then by doing substitution, the derivative of tangent will give you that secant squared. So you pick a substitution by changing the every other secant to tangent. Then you use the substitution of tangent x. And if that's not the case, and if you have a case where this power m is odd for the tangent, and you don't have an even power for the secant, then in that case you need to save one of the factors of the secant tangent. If the secant had power maybe 1, then what you need to do is you keep one factor of secant tangent, because that's the derivative of secant, and then in that case the power of the tangent, you've reduced it by 1, you pulled out one of the powers, so the tangent would have an even power. Then you can use the identity, the Pythagorean identity, and express every tangent in terms of secant, maybe secant square. Then in that case you use the substitution for secant, because the derivative of secant would be simply secant tangent. Okay, so let's look at this example. We check to see which cases is this. Oh, by the way, sorry, this is supposed to be 3. There we go. So let's say you can have this one to be even as well, but let's assume both of them are odd. Maybe that makes it more complicated. What if you're dealing with something like secant cube times tangent cube x dx? You look at the power for secant. If it's not even, so I'll move on to the next case. I'll look at the power for tangent. In this case it's odd. Then what you need to do is you try to save this factor of secant tangent. What do I mean by that? That means I'll try to write this integral, factor out the secant x and the tangent x, then multiply by whatever is left over. If you factor one of the secants, then there is secant squared x left, and if you factor out one of the tangent, then there is tangent squared x left. It doesn't really matter. This could have been 5, 7, whatever. So 5. Let me change it to 5. So you would have tangent to the 4th power left. Okay, so now dx, I can write this as secant x times tangent x. And the strategy is, because we want to use the substitution of secant, then I wanted to get rid of all the tangents. So I'll keep the secant squared x. Instead of tangent to the 4th power, I can write it as tangent squared x squared dx. Which means now I can use the Pythagorean identity and write this integral to be secant x tangent x times secant squared x, and instead of tangent square I can write secant squared x minus 1 squared dx. You may think it's too much, but after you do one substitution you will notice that it will become very simple. So if I pick the substitution u to be secant x, du becomes simply secant x tangent x dx. So this term secant x tangent x dx, that is simply our du. So you would have integral. You would have integral, that is the du. And secant squared, this is simply u squared, because every secant is, we call it u, and you would have u squared minus 1, the whole thing squared. So basically what you need to calculate is the integral of u squared times u squared minus 1 du squared. And then you square this parentheses, multiply by u squared. that becomes, I think everybody should be able to do that, so I'm going to skip ahead. You would get u squared times u to the power 4 minus 2u squared plus 1 du, and that is simply u to the power 6 minus 2u to the power 4 plus u squared du. This is to the power 6. Okay, what is that integral? The integral is u to the power 7 divided by 7 minus 2u to the power 5 divided by 5 and plus u to the power 3 divided by 3 plus some constant c. And instead of every u, you should now replace secant x. So you would get secant x to the power 7 divided by 7, or actually it's secant to the 7th power of x minus 2 secant to the 5th power of x divided by 5 plus secant, I could scroll down a bit, secant to the 3rd power of x divided by 3 and plus some constant c. And this is the result of our integration. It's too many terms, but the idea is not too complicated. You just try to write in terms of one of the variables that you already have the derivative of it. Okay, so this is in case if you're dealing with secant, tangent. Similarly, for cotangent, cosecant, it's exactly the same thing. Everything that we talked about for secant, tangent, it's the same thing holds for cotangent, cosecant. So I'm going to now focus on the case where the values inside the angles inside the sine and cosines are not equal. What do we do in this case? And it is very similar for if it was sine times sine, if it was cosine times cosine. What you only need to know is those identities that we mentioned earlier. If you have sine of A multiplied by cosine of B in this case. If you have this multiplication, what you need to know is basically this identity, sine A times cosine B. If it was sine A times sine B, you use the second identity and so on. Cosine A sine B doesn't really matter, you just interchange A and B. So the identity is 1/2 sine A minus B plus sine A plus B. So that I can write this identity here, 1/2 sine A minus B plus sine A plus B. Let's hope I wrote this correctly. I think yes, it is plus, if I remember correctly. Okay, then what do we do now? I'm gonna just replace A and B. This integral basically becomes, this is our A, this is our B. Sine times cosine. So you can write 1/2 sine A minus B, which is 4x minus 6x, plus sine A plus B, 4x plus 6x, that is 10x. Let me write this. And dx. And this 1/2 is multiplied by the whole thing. So I can write it outside, integral sine negative 2x plus sine 10x. Now ask yourself, can you calculate this integral? And similar to the cosine 4x that we need to do substitution for these, you can use substitution separately. Call negative 2x to be u, calculate the first integral, call 10x to be u, and calculate the second integral using substitution. If you do that, what you get is the integral of sine negative 2x is simply the integral of sine is negative cosine, so you'll end up with negative cosine negative 2x divided by negative 2, and plus negative, the 1/2 is for everything, so plus negative cosine 10x divided by 10. And this 1/2 is multiplied by all of them, plus some constancy. Simplify this, it becomes minus 1/4 cosine negative 2x minus. This is supposed to be positive because there's a negative 2 in the denominator. There we go. So plus times negative minus, so minus 1/20 cosine 10x plus some constancy. Okay, so therefore this is the integration. Double checking would be quite difficult because you have to go backward, and after you take the derivative you have to be able to do trigonometric identities to show that basically the result of the derivative will end up to be that. Okay, so just make sure that you use the correct integration technique. If it was cosine and cosine, nothing would have changed. It's just these function would be maybe sine, instead of sine it would be cosine, and instead of addition and subtraction you may have b minus a or b plus a. Doesn't really make any difference. Okay, so this is basically the technique to calculate the integration. What you need to do is mainly focus on which identity you're supposed to use and in which cases. Okay, try to do a couple examples and do your homeworks. So I'm gonna stop at this point.